Hey everyone. So today we're going to dive deep into Python object oriented programming. So I just quickly wanted to show the difference between O1 reasoning model versus deep research by ChatGPT. So I basically asked both O1 and deep research. What deep research is built on the reasoning models as well, but it thinks for way longer than the reasoning models. You can see the reasoning model thinks for 1 second here, and it didn't show right for some reason it disappeared. But this one thinked for 16, 17 minutes or something like that, or 18, I forget. But definitely over 15 minutes. It thought that long, and you'll see like the crazy report that it built. But you can see that I kind of prompted it the same. So I used the same prompt. So for O1, I said, I'm trying to learn object oriented programming in Python deeply. I already understand OOP, but I'm new to writing Python. Could you help me? And this is very similar, right? So you can see this is just the O1 reasoning model thought for about a second and just started outputting stuff. So I've already read over this. It's actually pretty good. Talks about some of the basic terminology in Python. Talks about how to define classes and create objects. Talks about classes and instance, encapsulation, inheritance, multiple inheritance, polymorphism, composition and aggregation, getters and setters, dunder methods, abstract classes, data classes, and meta classes and best practices. So you can see it's the next steps here. You can see it's a very small report, and it's pretty quick and concise for getting a quick overview of everything in Python. But I wanted a deep analysis on everything related to Python. This is stuff I already kind of know working with Python, but I want to have a way deeper. I want to explore way more breadth because I want to find things that I might not know and then dive deeper into those. So I just want to like a deep research, and this is research, but it's not deep. But it's still good and nice and concise. I read this in less than 20 minutes. I read this whole prompt or this whole result. But take a look at this. This might take me more than 20 minutes, and I'll definitely try to time myself because I want this video to be under an hour. But I asked the same prompt and I used the deep research feature. So I said, I'm trying to learn object-oriented programming, like I mentioned, and it said, that's great. To help you learn object-oriented program in Python deeply, could you clarify? So I was asked some clarifying questions. So do you have any specific topics you want to focus on, such as inheritance, polymorphism, encapsulation, design patterns, metaprogramming, etc.? Would you prefer a structured learning path? Do you want book recommendations? Are you interested in advanced topics? And I said, just give me a full detailed report and I could read it from top to bottom, and I can go from sort of an intermediate level Python user to an expert because I don't want to just know the basics, right? So you can see right here. So I'll compile a comprehensive report covering Python OOP from intermediate to an expert. This will include core principles, advanced concepts, best practices, and real world applications. I'll let you know when it's ready. And I'm pretty annoyed that it didn't show how long it thought it was thinking for, because you can see usually it does that. Look at these big reports. So usually it does this, but I don't know why that disappeared there. But the thing is, I was playing around with it, but look how massive this report is. But you could see that it is generated using the same one because there's all the different links that it's searched for. But look how massive this report is compared to just this small. Look at this. I already just got to the end, which is a small scroll. But look how deep this goes. And I'm gonna post this online for everyone to see. But look at this. This is crazy. So let's just spend 25 minutes going top to bottom from it and capture sections that we might think are interesting. And then from there, look at this report. It's so detailed. It's insane. How many characters is this? Copy. Word counter. So this was a crazy, holy crap, 20,000 word report. What is this? This one is way less for sure. I'm saying this one's like 1,000. Or let's say 3,000. See, 2,000. So 01 deep research outputted about 10 times more words. And let's see how deep it went. Yeah, that's just a cool contrast. Now let's actually read this report. 20,000 word report. Start from the top. So I'm going to put a timer and we'll get through. We'll try to just do a quick pass overview, and then I'll write down. I'll try to write down areas that I think are I want to deep dive into, and I'll spend another 25 doing that, and then I'll probably go to sleep for work. That's my plan. Get my notes ready. Cool. Start the timer. So brief history. It talks about the brief history and significance of OOP in Python. So, yep, that's cool. A nice history. So Python was created by somebody in this early 1990s. So it's been more than 30 years. It was designed as a multi-paradigm language with robust support for object-oriented programming from the start. Even early Python versions allowed defining classes, although new style classes unified the type system. And Python treats everything as an object. It's kind of similar to JavaScript. From numbers and strings to functions and classes and classes themselves. And you could see it's actually dropping links there. This means Python's approach to OOP is pervasive. Objects are a core part of the language's design. OOP has become significant in Python as larger programs demanded modularity and reuse. Wrapping data and behavior into class definitions helped organize code for maintainability. Python standard library and frameworks like Django heavily use OOP concepts, and if you get annoyed them saying OOP, I just don't want to say object-oriented programming. So they use OOP concepts such as classes for web requests, data models, demonstrating the paradigm's importance in real-world Python development. Python's philosophy blends simplicity with power, and its OOP reflects that. Unlike pure object-oriented language, Python doesn't force everything into classes. You can write procedural code, yet it fully supports OOP and encourages it for complex systems. Yeah, so you could do like functional, object-oriented. You could do a lot of different things with this. The flexibility allows developers to choose the best paradigm for the task, making Python a multi-paradigm language, supporting procedural, functional, and object-oriented styles. In summary, OOP in Python evolved to balance ease of use with the ability to model complex systems, and remains a fundamental tool. And Python is a dynamically typed language. I think most people mention that or know that here. So key difference between Python's OOP and other languages. Interesting. Okay, I think that part I want to dive deeper in is I'm gonna have a list on the side of things that I want to study. Get my galley draw on the side. So I definitely want to look at this so I can contrast with other languages I'm more familiar with, like Java when it comes to OOP. Wow, look at it. It gets deep. So what are the differences? They have dynamic typing and duck typing. No strict access modifiers. Simple syntax for classes. They use self. There's multiple inheritance. There's no method overloading. Everything is an object, so it's a unified type system. Okay. So, what are the core OOP concepts? So we have classes and objects. That's basically the same in most programming languages. So classes are blueprints for creating objects. A class defines a new type, including attributes. Yeah. When you create an instance of a class, you get an object. Yeah, this is regular. So it talks about how to define a class. Classes are the two main objects of, or are the two main aspects of object-oriented programming in Python terms. A class creates a new type where objects are instances of that class. Yeah. So when you define a class in Python, you typically use this is how you define a constructor. In other languages, you actually use the constructor is the same name as a class. For Java, that's the case, but it's different here. Cool. So we're diving deep into classes and objects, which is the two main things. We get into attributes and methods. So attributes are the variables that belong to an object or class. What else? Cool. Yeah, I already kind of covered this. Attributes and methods. Talks about encapsulation. So encapsulation is the OOP principle of bundling data and methods that operate on the data within one unit and restricting direct access to some of the object's component. The idea is to hide the internal representation of an object from the outside, only exposing a controlled interface. So in Python, encapsulation is achieved by convention and by using features like properties. Since, as noted, you cannot truly hide data. Yeah, you can't really hide data in Python. That is true. It's not like Python or Java where you can create private variables and then you can't actually access those variables. I mean, you could kind of do that in Python with the double underscore, like right this. But yeah, I think, yeah, it gets into that. So encapsulation it gets into encapsulation. So it's saying that we can combine data and behavior by defining a class and putting data attributes and the functions that manipulate the data. Yeah. This makes it cool. Then we could hide implementation details. A class ideally presents a clear interface and keeps the internal details hidden or less accessible. In languages like Java, you use private variables and only expose them via public methods. In Python, you achieve a similar effect by prefixing and by using properties to control access if needed. Python's approach to encapsulation is informal. Any attribute not intended for external use is typically prefixed with a single underscore. This is a convention recognized by tools and programmers. For example, will not import names starting with by default. Okay. Double underscores trigger name mangling, which makes it harder but not impossible to access attributes from outside. Okay. Yeah, it's talking about how to hide variables. So you could see, if I wanted to, I could still access that balance. But in Java, if you put private, it wouldn't be able to be touched. So cool. Talks about the very basic encapsulation and classes and objects. Now it's going to get into inheritance. Inheritance reduces a lot of code duplication. Let's see. Inheritance, single and multiple. Inheritance is the mechanism by which a class, called a subclass or child class, can extend or modify the behavior of another class, the base class. The subclass inherits attributes and methods of the base class, allowing code reuse and establishing a relationship. For example, if you have a base class vehicle and a subclass car vehicle, the car inherits all general vehicle properties but can only have specific features or... Okay. Nice. I think I'll definitely want to read into inheritance and single or inheritance specifically, because there's some intricacies when it comes to inheritance here and how it behaves. And I think that's important for understanding how it's going to behave. So, but one thing you might notice is there's multiple inheritance here. And in some programming languages, there's not multiple inheritance. I don't know if Java is still the case, but I think Java doesn't have multiple inheritance. Well, at least back in 2015 when I was, or 2016 when I was learning Java, it didn't have multiple inheritance. Wow, I'm getting old. It's 2025 and it's 2025 already and I was learning Java in 2016. That is nuts. It's almost been 10 years since I graduated high school. Whew. Okay, well, we're going to dive deep into that. So polymorphism, method overloading and overriding. So polymorphism means many forms. In OOP, it refers to the ability to treat objects of different classes through the same interface, relying on each class's specific implementation. There are a couple of aspects to polymorphism in Python. So there's method overriding. This is when a subclass provides a specific implementation of a method that's already defined in the base class, so it kind of overrides it. That's standard. Then there's method overloading. Then there's method overloading. In some languages, you could define multiple methods with the same name, but different parameter types or counts, and the compiler chooses the right one based on the call signature. Python does not support method overloading in the same class in this manner. If you define a method twice in a class, the latter definition wins and replaces the earlier one. Yeah, I just noticed that actually from reading that usually you'll just define one function with a ton of extra parameters, and depending on what you want to do, you're just going to just use the different parameters that you want instead of just overloading the function. That is interesting that they don't have that. I guess it kind of, what that leads to a lot of times though is one function that does so many different things. But yeah, that's actually interesting. I think that's also important. Holy crap, I might just have to spend this whole video just doing a quick overview because the report's so long. So abstraction. Abstraction is a concept of hiding complex implementation details and showing only the necessary features of an object. It's closely related to encapsulation, but while encapsulation is about restricting access, abstraction is about simplifying the interface exposed to the users. So you want to abstract away the details. Yeah, that makes sense. In Python, abstraction is often achieved through the use of abstract classes, ABCs, via the ABC module, or simply defining class APIs that don't require users to know how they work. For example, when you use a list in Python, you don't need to know how it's resizing or an underlying array or how methods are implemented. You just know that the abstract operations like append, remove, iteration, Key points of abstraction in Python. You can create an abstract base class. Yeah. That makes sense. So this is how you define abstract classes in Python. You pretty much, you import ABC, and then you basically inherit abstract base class for that, and you could define abstract methods. So now anybody who inherits from shape has to implement those abstract methods. Otherwise, they're just a regular abstract class and you can't instantiate them. I think you can instantiate them. Can you instantiate them? Does it say that? Yeah, cool. I'd never really seen abstract classes used that much. I see where it could be useful though, but I'd never had to use it that much. But yeah, I think it's good if you want to really enforce all the subclasses. It's good. So advanced. So now those are just basics. I think that's a decent basics. That's already a lot to read. Maybe I'll read it separately. But let's get into some of the advanced OOP topics. So dunder methods or magic methods are operator overloading. So Python's dunder methods, short for double underscore, also known as magic methods or special methods, are predefined methods you could define in your class to hook into Python's built-in behavior. So these methods start and end with double underscores, like init, string, add, length. By implementing dunder methods, you enable your object to support Python language operations in a natural way. That makes sense. So for example, if you want to overwrite the toString function, like the print, like if you want to overwrite the way an object prints or define the way an object prints, usually you'll use these dunder methods. So it talks about it here. So these are the dunder methods that you can override and actually implement. So in it, this is the constructor. Represent should return an unambiguous string representation of the string. This str returns a user-friendly string representation, so used for like print. Then if you want to define how the length function works, you can define it here. And I find these very useful when I'm building data structures from scratch. And if I build like a linked list from scratch, or yeah, if I build a linked list from scratch, right, and I want to be able to return the length, I can specify a length property in my class that I increment and decrement as I add nodes to my linked list. And then I could easily print the length of the linked list. But you have to be able to tell the length function where to look. So usually you'll override length and then choose the property or the attribute that you created on that object. These methods are magic because Python calls them behind the scenes. For example, when you write a plus b, if a is an instance of class that has add, Python will do this. Okay, yeah, that's kind of why they're called magic methods. I didn't know that they're also called magic. I just call them dunder. Now you can do, okay, cool. Let's move on to the next part. Oh, I didn't even know Python has static methods. I see. So by default, methods in Python classes are instance methods. They expect a self and operate on specific object instance. Python also provides two other method flavors. They offer class methods and static methods, which are used using the built-in decorators. So Python really likes to make use of decorators in order to change behavior of things instead of using keywords. For example, in Java, use a lot of keywords like private, right? But here they like to wrap functions in decorators, and it's more like, yeah, it's a bit different. It's interesting as well. And I also want to learn more C++, so I'm gonna be spending more time on that soon too. Class and static methods. Okay. So class methods. A class method is a method that's bound to the class and not the instance. So when you declare a class method, its first parameter is conveniently named class instead of self, and it refers to class. When the method is called, the class method can be called on the class itself. But do we still have to... Okay, we still need to add the decorator and then it accepts the class. Interesting. So pretty much after that, you can just... Yeah, when you define class methods, I don't think you'll be able to access instance level variables. Well, yeah, probably because self is not even there. So these class level attributes are shared by all objects of a specific class. So static methods. A static method is like a regular function that happens to live in the class's namespace. It doesn't receive an automatic self or class. You declare one with static methods. Static methods cannot modify object instance state or class state unless you explicitly pass in objects to them. They are utility functions that logically belong to the class. So when do we actually need to use this? I feel like we don't really need to even do those static methods because Python is also functional, so we could just define add as a function and we don't need to wrap it in a class that's just going to be static. So cool. Yeah, we have class methods. Nice. Now I know how to define classes. Static methods. They cannot access class yourself unless you explicitly pass them. They behave like plain functions but are contained in the class's scope. Instance methods. This is what we're more familiar with. Honestly, I mostly just use instant methods. Never really get into class and statics. So it talks about when to use. Use an instance method whenever the method needs to access or modify the object state. Use a class method for factory patterns or methods that logically operate on that class's level. For example, if you have an ORM class model, a class method could be modeled from that creates the DB and returns an instance of the appropriate class. You could even decide to return an instance of a subclass depending on the data. And then we use a static method for utility functions that don't need self or class but relate to the class conceptually. Okay. Use a class name. Okay, cool. Nice. So it looks like in Python there's just instance variables, class variables, and static variables. And you could, of course, just name like direct functions. So now it's talking about how to actually use them, but I'm going to skip over that. Python properties, property decorators and descriptors. Okay, properties are just like this. Properties basically allow you to access properties within here. So for example, if I called temperature.celsius, it will return Celsius. It's kind of a bit weird, but yeah. We could create getters. It's essentially, if you're familiar with Java, it's essentially how Python does their getters and setters. You can get and then set. Let's skip over that for now. What are descriptors? While property is a high-level convenience, Python also allows crafting custom descriptors by implementing the descriptors protocol in the class. For example, you could make a descriptor class that logs access or enforces types across many different classes. What? What's a descriptor? Never actually heard of this. So while property is a high-level convenience, Python allows crafting custom descriptors by implementing the descriptor protocol in a class. For example, you could make a descriptor class that logs or enforces types across many different classes. So we create a class and when we X, I don't even get that. Yeah, I've never had to do. Yeah, I've never heard of descriptors before. So maybe I'm gonna prompt GPT to teach me about descriptors. Because but they say it's an advanced topic that it's not really used. It's used in ORMs and stuff. Look, it says yeah. Meta classes and their use case. So, meta classes and their use case. Meta classes are one of the more advanced and powerful features in Python's object model. A meta class is put simply a class of a class. It's the blueprint for creating classes. Just as classes are blueprints for creating objects, in Python, classes are themselves Okay, wait. What is going on? Classes are themselves objects of type by default. Or what? What is this? Metaclasses are one of the more advanced and powerful features in Python's object model. A class of a class. It's the blueprint for creating classes. Okay. Just as classes are blueprints for creating objects. So we can make a blueprint for creating classes. In Python, classes are themselves objects of type by default, or a class of type. By changing the meta class, you can customize class creation. When you define a class in Python using the class keyword, Python executes the class body and ultimately calls a meta class to produce the final class object. Normally, this meta class is type, the built-in meta class that knows how to build normal classes. However, you can control this process by specifying a custom meta class, either by using meta class. What? If classes are objects, meta classes are the classes of those objects. For example, if foo is a class and foo produces an instance, then the meta class of foo defines how foo is created and what it can do. Okay. Interesting. So it's when we want to automate how classes are created and class behavior. That is interesting. I never got this deep into a language before. Let's see the use cases. Okay. So we can use meta classes to enforce certain behaviors or constraints on classes. We can automate boilerplate. So you can have a meta class that automatically adds methods or attributes to classes, removing repetition. For instance, a meta class could automatically add str or represent based on class attributes, or it could add. I see. Because yeah, when you just create a class, it's just gonna default the way str and represent is built is gonna be default behavior. But if you want to sort of optimize that and make it, when you call class of a specific type, to like not generate str and represent the same way, you could do that with meta classes. That is crazy. Okay, that's we don't want to dive deep into that, but that's crazy. Meta classes versus some things that can be done with meta classes, like class, can be done with class decorators, a function that takes a class and returns a class. Class decorators are simpler but less powerful than meta classes. They can modify or wrap a class after it's created, but cannot control the creation process itself. Meta classes are an advanced tool. They add complexity and can make code harder to understand because the class definition can have hidden behavior. The famous saying is meta classes are deeper magic than 99% of users ever need. So wow, we're really getting into things that are really deep, that we might not even know about, or that I might not even be shown in a regular report, or if I was just looking in the internet. But I'm so happy this thing pulled that out. Didn't we already go through abstract base classes? What? I swear we went through that. Let's skip that because I'm already familiar with abstract base classes. Okay, the method. Okay, the method resolution order for multiple inheritance. We're like almost halfway. Okay, best practices. We're gonna write down. Let's scroll through to see. Let's get a check of where we are, so we don't run past the hour here. So we have best practices. So solid. Composition over inheritance. Avoid, these are common pitfalls. Design patterns. Dude, this thing is going crazy deep. Practical application and case studies. Wow, it's even doing case studies? Performance considerations and optimizations. It goes into testing. I really want to dive deep into testing. I'll probably spend some time reading into that as well. Because that's actually really more important. So I'll definitely look into more testing. I think decorators and stuff are important. And then resources for further learning. This thing goes really deep. Because decorators are really important for things like logging as well. And it talks about all the different open source projects to study if I want to study open source projects. Maybe this year I'll get into open source programming. Like working on open source projects. But wow, that's a really good overview. I think what I want to dive deep into is testing, because that's going to be important for everyone here. Because now we have basics of OOP. And actually, that's probably a different video because I want to focus this on just straight object-oriented programming. But let's see. But it just defines everything. Yeah, maybe we'll just keep reading down this thing. But I'm gonna take a quick break, and then we'll probably spend the last 20 minutes looking through the best practices in OOP for Python. But all right, I'll be right back. All right, let's get into method resolution ordering in multiple inheritance. So, wait one sec. Let me just quickly make sure my sound is okay. Okay, method resolution ordering. So when multiple inheritance is involved, an important concept is the method resolution order. The MRO is the order in which Python looks for a method or attribute in a hierarchy of classes. So pretend, let me get a Scally draw. So I think how we can look at this is pretend we have one like foo, and it takes in from base 1, and it also takes in from base 2. Python searches. So what happens? The MRO is the order in which Python looks for a method or attribute in a hierarchy of classes. In single inheritance, this is simple. Python searches in the class, then its base class, and then it just keeps going up. In multiple inheritance, Python uses a specific algorithm, C3 linearization, to linearize the class hierarchy into a single list that respects the inheritance relationships and orders. Interesting. Python's MRO algorithm, C3 linearization, ensures that the order is consistent and respects two main rules. A child class is checked before its parent classes, and two, if a class inherits from multiple classes, the order of searching those base classes follow the order in the base class tuple in the definition. So you could actually get you can get an MRO to see the how it actually inherits, and because when you use a function, pretend I say hi, and that's defined here, right? Pretend I have foo, a special foo, right? If I call hi on this, it's gonna look up the chain. If there's no one here, it might look there. Like it's basically which hi do I choose, right? Obviously, I want to check here. Then I would want to check here. But if it's not in there, I'd want to check like these two as well. So, but now it gets weird because it splits off into two. So that's kind of what this is describing. So yeah, there's this multiple resolution and it follows the C3 linearization. That goes pretty deep. I don't know if I need to care about that right now. But let's get into the juicy part for the last 19 minutes, which is the best practices in OOP for Python. So first, solid principles applied in Python. SOLID is an acronym for 5 fundamental object-oriented design principles introduced by Uncle Bob, aimed at making software designs more understandable, flexible, and maintainable. These principles can be applied in Python just as in other OOP languages. Though the dynamic nature of Python sometimes offers alternative ways to achieve similar ends. The solid principles are single responsibility principle. A class should have only one reason to change. In practice, this means a class should only have one job or one responsibility. If a class is doing too many things, so handling business logic and also managing database operations, it violates SRP. To apply SRP in Python, break down classes that have multiple responsibilities into smaller focused classes. For example, if you have file manager class that reads and writes files and also compresses them, consider separating the compression into a different class or function. SRP leads to more classes but is simpler and more focused. In Python, where creating classes is easy and not verbose, following SRP is quite feasible. That makes sense. I should do one of these with like React, super deep in React, because I spend a lot of time doing React stuff. So, but this is really cool. SRP, single responsibility principle. That makes a lot of sense. Like, make sure objects and classes have one responsibility. Open close principle. Classes should be open for extension but closed for modification. This means you should design classes that can be extended without modifying their existing code. In Python, rather than changing the code of a class to add features, you prefer adding new subclasses or using hooks. For example, if you add a function with giant if-elif, if you had a function with a giant if-elif to handle different cases, you might refactor it to use polymorphism. You create a base class and subclasses for each case. Now adding a new case means adding a subclass, not changing the core logic. That makes a lot of sense. So yeah. Classes should be open for extension but closed for modification. Okay. That makes sense. That makes a lot of sense. Yeah, definitely I've seen lots of code violate this all the time. Like, these solid principles are best case scenario, but sometimes you just don't. It just doesn't get there. But it's good to know. Honestly, you just need to keep refreshing your stuff on this all the time. So if you had a function with a giant if-else, you might refactor it to use polymorphism. Create a base class and subclasses for each. Yeah, that makes sense. Python's duck typing and dynamic features allow extension by monkey patching or by registering new behaviors like the register. What the heck is monkey patching? I have a bunch of questions on the side. Cool. Liskov substitution principle. Subtypes must be suitable for their base types. In other words, if class B is a subclass of A, then anywhere an A is expected, B should be acceptable without breaking functionality. So if B is a subclass of A, anywhere where A is accepted, yeah. Subtypes must be suitable for their base types. Okay. Yeah, that makes sense. So anywhere where A is expected, you should be able to pass in a more general function and it should work. That makes sense. Because if A is expected, it's expecting the most general case. So the principle demands that subclasses only extend the base class's behavior in compatible ways rather than changing it. A classic violation of LSP is a subclass that overrides a method to throw an exception. So when that method is called, then that subclass can't truly stand in the base class. In Python, LSP means designing class hierarchies where subclasses fulfill the contract of the base class. Even though Python doesn't have explicit interface contracts, you as the developer define what the methods do, and subclasses should honor those expectations. Okay, I kind of get that, but I'm gonna go over to the next one. Interface segregation principle. Clients should not be forced to depend on methods they do not use. So clients should not be forced to depend on methods. This principle advises creating specific narrow interfaces. Okay. This principle advises creating specific narrow interfaces rather than one large general interface. In Python, we don't have an explicit interface, but the concept can be applied by using multiple ABCs or mixins instead of one giant one base. What are mixins? Honestly, I see that a lot when I'm looking over a code base, but I actually don't know what that is. In Python, we don't have explicit interface declarations, but the concept can be applied. So, for example, instead of having a huge vehicle base class with every possible method, start, stop, you might have separate abstract base classes or mixins, and only have classes implement, derive what they need. This is to avoid fat classes that impose unused members on subclasses. But respecting it also, okay, honestly I don't understand these principles, but it's interesting. This solid, I never knew that we want to be applying solid principles to Python. Dependency aversion, I like this. Depending on the abstractions, not on concrete implementations. Depend on abstractions, not on concrete. The principle has two aspects. High-level modules should not depend on low-level modules, but should depend. High-level modules should not depend on low-level modules, but should depend on abstractions. Abstractions should not depend on details. Details should depend on abstractions. In practice, dependency inversion principle means that rather than a class instantiating its own dependencies, you should accept those dependencies from the outside, perhaps via constructor or setters, and ideally refer to them through the abstract interface. In Python, DIP often shows up as passing in file-like objects, not assuming a specific implementation. For example, a report generating class shouldn't hardcode writing to open. Instead, it should accept any file object to write to. That allows dependency injection. Okay. Well, I need to study more solid principles, but whatever. Let's get into the next part. Composition versus inheritance, and what else do we have? Common pitfalls. This might go a little bit over. And I think, yeah, after we get through that, we don't really need to. We can cover some of the other ones in separate videos, but just to keep this nice and short, let's walk through. avoiding common pitfalls in OOP. Or sorry, I want to also read this composition versus inheritance. So inheritance and composition are two fundamental approaches to structuring object-oriented code. Inheritance is a relationship, where composition has a relationship. This is a well-known design guideline. Favor object composition over class inheritance. I've heard that even for Java. Both mechanisms have their place, and Python makes it easy to use either. When to use inheritance. When there's a clear hierarchy and is a relationship. So if class B is a specialized form of class A, inheritance makes sense. For example, car and vehicle. Inheritance expresses that naturally and allow code that works on vehicles to also work on cars. Yeah. When you want to reuse code from a base class in a controlled way and possibly override parts of it. Inheritance lets you inherit. When designing frameworks, you might use abstract base classes and require users to subclass them. Implement certain methods. Yeah, that makes sense when designing frameworks. When to be cautious when inheritance. If the subclass only somewhat fits the base class, inheritance fits the base class interface, but not entirely. Making square inherit rectangle might lead to issues in rectangle. I see. Inheritance can sometimes lead to a tight coupling between the base class and the subclass. If the base class implements changes, subclasses may break. Deep inheritance hierarchies can become difficult to manage. I've seen this for sure. So in Python specifically, inheritance of built-in types has some quirks, though much improved in Python 3. Sometimes it's recommended to wrap built-in type rather than subclass it. For example, subclassing lists versus having a collection. Okay. Composition means you build classes that contain instances of other classes to achieve their functionality, rather than inheriting it. So for example, instead of class inheriting from engine, that doesn't even make sense because car is not like a more specific version of engine. Car could have an engine object as a component. Since a car has an engine you can swap out components easily. If a car has an engine interface, you could have a diesel engine or electric engine chosen at runtime or configuration. This is harder when inheritance, which is a static relationship. That makes sense. Avoid inheritance pitfalls. With composition, you avoid the complexities of MRO, which is the multi-resolution order, and potential unintended interactions between base and subclasses. You control how the composed objects interact explicitly. Yeah, multiple inheritance is just tricky. Instead of inheriting with two classes to get both behaviors, you might have one class and give it two components, each handling part of the behavior. So encapsulation. Composition can lead to better encapsulation. The inner working components are hidden behind the well-defined interface. So drawbacks. It can result in a bit more forwarding code. Methods that simply call methods on internal objects. For example, text editor has a clipboard object and you want to do clipboard copy. You need to write the forwarding method. Though this overhead is usually minor, it doesn't automatically provide polymorphism in the way inheritance does if you have composed object. So yeah, I guess, okay, just need to keep in mind to prefer composition over inheritance if possible. And there's examples of that. So what are the common OOP pitfalls? Misusing mutable definitions, or misusing mutable default arguments. Although not specific in OOP, this often bites Python programs in the butt, or programs with methods. So misusing mutable default arguments. Although not what? So though not specific to OOP, this often bites Python. A classic mistake is defining a method or function with a mutable default value. So if it's mutable, this creates a class attribute-like behavior unintentionally because the default list is created once and shared across all calls. It means every instance without an explicit list will share the same list. That's crazy. I didn't even know that. This pitfall is particularly relevant in constructors for things like default list or... Dude, that is a crazy one. I'm gonna write that down. That is a crazy... Dude, this thing's crazy for knowing that. Class variables versus instance variables. In Python, if you assign to a variable in the class body, it becomes a class variable. If you intend each instance to have its own copy, you must do self.var. So... Okay. Not calling super in subclasses. When overriding init in a subclass, it's common to forget to call the base class's method, especially if that base class does important setup. So, not calling super in subclasses. When overriding init, it's common to forget to call the base class's method, especially if the base class method's important. Yeah. In Python, there's no automatic constructor chaining like in some language. You have to call it. Forgetting to do so means that the parent's initialization never happens. Okay. Forgetting to do this can mean the parent's initialization, which might get up, never happens, leading to bugs. Similarly, for other methods that are meant to augment rather than completely replace base functionality, calling super allows the base behavior to occur. Okay, always using super is crucial, so yeah. Okay, that makes sense. If you implement ensure you follow expected conventions. Okay. Okay, using self wrong. Newcomers sometimes omit self in method definitions or calls, which is a syntax error or logic error. Remember, self must be the first parameter of instance methods, and you don't pass it explicitly when calling the method. Another mistake is using a variable without self inside a method, which will just be a local variable, not affecting the object state. Okay, not properly understanding state, I guess. Name mangling and private variables. Misunderstanding is and shallow versus deep copy. Memory leaks, over engineering. Yeah, I think this is already gonna hit an hour, so I don't want to upload a video that's longer than an hour. But look at this crazy report that Python generated for us. I think it was really good. Definitely learned a ton from this. And yeah, hope you all enjoy the video. This video is going to be deep research on object-oriented programming in Python. I'm definitely going to do more of these videos and explore a bunch of different topics, because now that I paid for this, I need to use it up. So cool. I'll see y'all in the next video.